we've been toying around with this word energy for a little bit. And I
Uh-huh.
was wondering if you could explain what that is, because it's
Yeah,
it,
it's
to
a
someone who doesn't really study physics, it might be a very empty term.
yeah. So energy, I think, like at the high school level, we talk about it as the ability to do work.
Okay.
So if something has a lot of energy, you can channel that one way or another to do something, and that's kind of where the the story ends at like the high school level,
Which isn't very much, actually.
which isn't very much. Yeah, and it's kind of, I think it lacks the exciting, like beautiful part of it, which is, it goes back to this theorem by Emmy Noether. Um, so when you write down this thing in this mathematical equation for some system called the action, and then I talked about symmetries of the action leading to conservation rules. The symmetry that leads to the energy conservation rule is a time invariance. So it's the fact, like the way it's popularly said is like, if you do a physics experiment now, or you do it in 5 minutes or in 2 hours, the physics is the same. The result is the same. And that necessarily means that there's some quantity that is conserved throughout the process. That quantity is what we call energy. So there's a deep like relation between time invariance and energy conservation.
Time invariance?
Yeah.
Okay.
As in like things don't change if you do them now or later or in the past.
In a physics standpoint.
Yeah, like I can drop this pen now and I can drop it later in the same position and the same thing will happen. In a kind of ideal world. Of course,
Yeah.
there are air currents and things that
Yeah,
like
yeah.
complicate this, but yeah.
Okay. And another thing that is studied a lot in physics and is gravity. And I was wondering if you could kind of demystify what gravity is in I guess a cosmological sense.
In a cosmological sense, I could say, okay, I can give two kind of descriptions that I think are interesting. One is Newtonian gravity, which is you have this something that's called a force that depends on two masses at some distance. So you have a mass, and this is like the charge of the gravitational force. And the higher the mass, the higher the force between these two objects. That was the Newtonian way of looking at gravity. And it falls off as like 1/r². The way that we look at gravity now is that we imagine this geometric thing called space-time, and everything is essentially just moving on straight lines, or what are called geodesics. So they're just moving in straight lines all the time. And gravity is sort of like an apparent force because they're moving on straight lines on the space-time, but the space-time itself is bent. So when you bend it enough and you push something in a straight line, it just looks like it's being curved around. So we see it as a force, but really it's not a true force in the same way that like in particle physics we talk about forces. And we see it as like a manifestation of some geometric structure in space-time. And I think that's a cool way of looking at it, but it's also very different and a very different framework from the way we think about a lot of other things in physics.
Right. And this is actually something that I've been wondering forever. So if you like Google, like go on Google Images and you Google like black holes and like their density, and you see this like, you see Earth and you see like this concave shape around, and then you see like black holes kind of go down.
Sure, yeah, I know.
You say kind of.
No, I know what you're talking about. Yeah.
What is this, like, how can someone actually kind of visualize this kind of depth thing if, like, space is it's kind of like being in the ocean, like these 360 degrees that you can go everywhere, right, in all directions.
Yeah.
But how can it be, like, this flat plane necessarily?
It's not, so that's the thing. That's a visual aid.
Representation,
Yeah, but it's not actually bending in 2D like that. That's just the only way we can draw something bending in 2D is that way. But really, the thing that's bending is not even 3D. It's the 4D space-time itself. It's the
Right.
whole 4D object. So you don't actually, at least as far as I know, it's including the time is, yeah, because you have some coupling between time and space. Um, but it's hard to draw that. It's really that's the answer I can give you. It's just like the picture you have in your head is like a lower dimensional representation of what we
Literally.
think is happening. Yeah, it's literally yeah.
Okay. And what is the relationship between time and space? How is time actually a physical dimension?
That is a good question. What is the relationship between time and space? Well, okay. It's a dimension that has an interesting property, right? So like we have three physical dimensions. I can move forward, backwards, I can move left and right, and I can move up and down.
XYZ.
X, Y, Z. And those are like degrees of freedom I have. But I can only move forward in time.
Right.
I cannot move backwards in time.
Is that the famous term, the arrow in time, that people sometimes use?
It's related to that. Yeah, I mean the arrow of time. It's something people talk about a lot, and people really wonder about this stuff.
Okay.
We don't know. We don't have a solid answer, I think, as to why the arrow of time is only forward, for example. But when you imagine it from our like human brains, it's like, can you even imagine a world where it wasn't only forward?
No.
So then, now we leave this realm of physics and we start wondering, like, even if it was the case that you could move forward and backwards, and we couldn't just computationally comprehend this in our heads, you end up with a world that can only move forwards in time according to our perspective.
Right.
So this is like beyond physics, but it's an interesting question.
What makes you say that's beyond physics?
Well, in the sense that what we're talking about is like untestable, right? So how do you test how our perception changes the kind of way we view the universe? Is the universe happening and we're perceiving it, or is it kind of we're trying to make sense of what's coming in via our senses? And our senses are, in this sense, like also expanded by experiments and detectors. Like those are just expansions of our senses, really.
Right.
So how can we imagine something that has nothing to do with our senses?
It's a good question. Not even the psychologists have an answer for that.
Yeah, I don't think it's not a physics question. It's just like a kind of philosophical, like, is the world out there actually this way, or is it because we can only allow ourselves to be, we can only perceive things in a particular way, that we see it that way?
So just to clarify, you're saying that the relationship between time and space is a philosophy question, or just...
No, I don't know how to answer that question. I actually don't know how to answer that question well. I guess I would say that.
Does anyone have a good answer? Or
I'm sure people have good answers. There are a lot of smart people in the world.
Right.
Yeah.
Okay.